guys, this is the last video for chapter 9, so that's exciting. Only one more chapter left. This one we're going to talk about bond energy, enthalpies of formation, and then we're also going to talk a little bit about lattice energy, but that's going to come more into play in Chem 2. Alright, so for bond energies, that's the amount of energy it takes to break 1 mole of a bond in a compound. Okay, we have already talked about this. We talked about this in chapter 5 just a little bit, but now we're really going to focus in on it. So this is a very important equation, the bonds broken minus the bonds formed. This one is actually going to be reactants because we're breaking the bonds of the reactants and we're forming the bonds of the products. Okay, all values are going to be positive, so that's the reason why it's not final minus initial, because of the negative sign needing to be where it is. All right, if you recall, there is a trend for the bond energies. Remember, the more bonds there are, the stronger the bond. So a triple bond is going to have a higher bond energy than a single bond. Also remember, shorter bonds will be the triple, longer bonds will be the single. Okay. And then bonds also get weaker as you go down a column, and that's because their attraction isn't as much. So it's about that. The ZEF, the nuclear effective nuclear charge. Okay, here's an average table of bond energies. I would suggest you either have this page readily available. I am also going to post one. The biggest thing on this page is that you note that CO2, specifically CO2, those double bonds are 799. Normally, a double bond of CO is 736. So you just need to keep that in mind. So here we're showing as we break the bonds in methane and chlorine, we break them and then we form new ones. All right, so the biggest thing with bond energies is that you have to draw them. This is why the Lewis structures are so important. Once you've drawn them, you need to pull your values from that table from a couple slides ago. So there's the value of CH, but there are 4 CH bonds. And then 464 is the value of OH, but there are 2, there's 4 because there's 2 and 2. Okay, so that's bonds broken, that's reactants. And there's the chart again. We do the same thing for bonds formed. So hydrogen bond is 436. Carbon dioxide's double bond of CO is 799. And then we do our math, reactants minus products. Okay, it's really 170 kilojoules. This is the same. If you wanted this to have the same sig figs, it'd be 170 kilojoules. Don't forget about sig figs when all this comes into play. But remember, when we subtract and add, we only pay attention to the numbers after the decimal, and here there's nothing after the decimal. So it doesn't have 4 sig figs, it has 3 sig figs. Specifically because there's nothing after the decimal, we want it to be a whole number. Okay, so here, it's more like it. We've got methanol, write out a balanced equation for the combustion of methanol. So CH3OH plus O2 yields, remember, combustion yields water and carbon dioxide. We do need to balance. Remember, you should start with a coefficient of 2 in front of your hydrocarbon. And then I've got 4 oxygens plus 4 is 8, so this needs to be a 3. Okay, and remember, the biggest part of bond energy is that you have to draw them. I am going to draw them above here. So I've got 2 CH, I don't want that H there. OH plus 3 O yields 4 H2O plus 2 CO2. All right, so here are our values. Remember, this is reactants minus products. I'm going to do delta H equals. I've got 3 CH bonds, which is a single bond. So CH is 414. I've got 1 CO single bond, 360. Plus 1 OH is 36. OH 464. Plus 3 of the O double bonds. There they are, 498. Oh, actually, I forgot to times my methanol by 2. So this one is 6, this one is 2, and this one is 2. Okay, it's very important. And I've got OH is my 464, so I have 8 of those because remember I've got 2 per. So I've got 8, 464, and I've got 4, 799. Okay, I do generally suggest that you do each side by itself, and then you do the subtraction. So I get 5,626 kilojoules minus 6,908 kilojoules. So this one will be exothermic. Negative 1,282 kilojoules. Okay. That should make sense because this is kilojoules per mole. Because it specifically says kilojoules per mole. This is a combustion reaction, and those tend to be highly exothermic. So if you have a combustion reaction that's not an exothermic, you may want to reevaluate your numbers and make sure that that's correct. Okay, if you want to work this last one, you're more than welcome to. All right, standard state is going to be super important as you go into Chem 2 because it's going to appear a lot. So standard state means it's got specific conditions. It's at 1 atmosphere for the pressure. It's normally at 25 Celsius or 298 Kelvin. Also, normally it's 1 molar. Okay, this little degree sign here means that it's at standard conditions. Okay, so standard state, 1 atmosphere, 25 Celsius, 1 molar. The standard enthalpy of formation is the enthalpy change from the reaction forming 1 mole of a pure compound from its elements. This is super important. It's also super important to note this bottom statement. Okay, first off, the elements do have to be in their standard state, so whatever state they're found in, that's what state they come in. So like oxygen is going to be O2 because there's diatomic. If you have forgotten the diatomics, they are the gens. Hydrogen, nitrogen, oxygen, and then the halogens. Again, these are the diatomic molecules, okay, and they all come in 2s in their standard form. Every other element comes single in its standard form, except those, the diatomic molecules. Okay, everything that's found in its standard form as a pure element is going to be 0 kilojoules per mole because that's how it's found. It will not have a value on the table, and you'll see the table in a minute. So here is a table. I will post a much more thorough table for y'all to view, but you're more than welcome to use this one as well. Some of the values might be slightly off, but they should be pretty close, and it'll be okay. All right, so write the equations for the formation of magnesium carbonate and glucose with their respective elements in their standard states, and then find its value for each equation. So we've got Mg, magnesium starts as solid, plus carbon solid, plus 3/2 O2 yields, and that's a gas, MgCO3 solid. All right, so once we're at this point, we're going to go back and look at our chart. Oh, sorry. Okay, so we are looking for magnesium carbonate. They are alphabetical. And of course, it's not on this chart. The chart that I'm going to give you has much more thorough values. Okay, so it's going to have everything you could ever want for the most part. Okay, so you would just go to the chart at that point and find magnesium carbonate on it. Okay, again, it is important to note that here we've got this 3/2. This is really the first time you're seeing halves besides in Hess's law on the last video, and that's because we need it to equal whatever the other side is, and we can only make 1 mole of that formed compound. So I've got to have fraction coefficients. Okay, so for B, I've got carbon. I have 6 of them. I've got 6 hydrogens. That's a gas. And I have 3 oxygens. That's a gas. And that makes glucose. Okay, I don't know if glucose is on the chart. Glucose is on the chart, so its heat of formation is negative 1273 so delta H of formation, negative 1273.3 kilojoules per mole. Okay. If y'all need more practice, you're more than welcome to do that one. But these aren't really overly hard. You just need to make sure you know the coefficients and how to make them balance to equal that one compound for your products. All right, so we are going to start doing delta H for the reaction. And this is always going to be products minus reactants. This is just the sum of, don't forget your coefficients like we were using for your bond energies. Okay, so normally delta means final minus initial. It's only different for bond energies. Okay, so we're going to need our chart for this. Let's see, is it going to show me a chart? Okay, so on a test, this would be more like what you'd be given if we were in the classroom, okay? And you just do products minus reactants. We're going to do 4 times that NO because that was our first product, 6 times our water, and then our reactants are ammonia, 4 of them, and 5 oxygens. Remember, oxygen is 0, and that's because it is a free element. That's its standard form. Okay, and you do products minus reactants. This one happens to be exothermic. You do need to get used to telling me, is it endo or exothermic based on that delta H value? Okay, so let's do this one. I've got products minus reactants. So delta H is equal to, so I'm going to go back to my chart. So I've got 2 times 0, which is our iron, minus our reactants are 2 times aluminum, which is 0, plus that iron 3 oxide. So what I'm doing is going back to that big chart. They didn't give us a big chart. There's going to be one. Surely. Apparently there's not a large chart. Oh, it's much farther back. Sorry, y'all. So I'm looking for aluminum oxide and iron 3 oxide. Neither of which are on this list. Okay, so this is gonna take having your chart, which again, I will post one, but because I'm in this slide, it won't let me like go out and then come back in easily. So I'm just gonna put whatever Al2O3 is, that one goes here, and then Fe2O3 goes here. whatever that value is on that delta H chart. Again, I will post that. Okay, so this one requires us to do the delta H equation because we need delta H out of it, and then we do our enthalpy stoichiometry. So here we're finding delta H with our values. Again, they're all going to be on the chart. And then we do our enthalpy stoichiometry to get the mass out of it. All right, last major topic of this chapter is lattice energy. It is important to know, or crystal lattice and that ionic bonding. Crystal lattices are the structures for ionic compounds. And it's because they kind of form a very rigid structure. They're held together by these electrostatic attractions, which are just because of the positive and negatives of the cations and the anions. But they're kind of every other compound or every other element is a cation or an anion. And so they're just attracted to each other because opposites attract. Okay, that extra stability is because of the lattice energy. And lattice energy is released when the solid crystal forms from separate ions in that gas state, and it's always going to be exothermic. Yes, exothermic. And it is super important that you remember that this is only for ionic compounds because you have to have ions for this lattice energy to happen. So it is going to be, the Born-Haber cycle is a very common reaction that's used for lattice energy and just thermochemistry in general. Okay. But here is what I'm talking about for that lattice energy. We've got the anions or the chlorine, those are the green ones, and then the purple ones are the sodiums, the cations. Okay, and they're just held together by that electrostatic attraction. So here it's showing us the process. Okay, I'm not going to ask you specifically like how lattice energy works. You will use a Hess's law for it though, just because it's got lots of steps. All right, so that the trends in lattice energy, there's going to depend on the size of the ion. So go back to your atomic radius trend because that's going to come into play. And that force of attraction between those charged particles, so that positive and negative cation and anion, are going to be inversely proportional to the distance. So the larger the ion, the weaker the attraction. And that's because it's farther from the nucleus, so it can't pull those electrons towards it. And then weaker attraction will mean weaker lattice energy. So bigger ions mean smaller lattice energy. There it's an inverse relationship. Okay, so here's an image. Remember, as we go down the periodic table, atoms get larger, and they're compared with the same atom on the other side. So as you can see, as the atoms get larger, that lattice energy is getting smaller as we go down the column. And then for the charge is also going to come into play. So bigger charge means stronger attraction because there's more electrons attracting them to one another. So a +2 -2 charge is going to have a stronger lattice energy than a +1 -1 charge is going to have. And that's because the bigger charges mean stronger attraction, which means larger lattice energy. So we are comparing them in increasing magnitude of these. Okay, so first thing you should do is look at charges because charges are going to matter and so are the size. So first let's look at charges. We've got strontium oxide and calcium oxide. So those are both 2s. So I'm going to put 2 above those. I'm going to put 1 above those for charges. Okay. Now that we have charges, I know that calcium oxide and strontium oxide will be the biggest ones. And then KBr and KCl, potassium bromide, potassium chloride, will be smaller. Okay. Remember, the bigger the molecule or the bigger the atom, the weaker the attraction. So KBr is first because Br is farther down, so it's a larger atom. Then KCl. So then we're left to strontium oxide and calcium oxide. Calcium is smaller than strontium, so strontium will be weaker. Also remember, you got to make sure you know which order is which. Increasing means smallest to largest. Decreasing means largest to smallest. And then they checked it with values, but you don't need to look up their values. You just need to look at the charges and the size. Okay, so again, charges first. That's the easiest. Once increasing, so CaO is going to be last. Okay, so LiBr and KCl. So Li is really small. It's going to be pretty close. And Ki, so Li is going to be larger. And Ki is going to be, because Ki, both K and I are larger atoms than Li and Br. Okay, one more. Sorry, my dog wants to play with the other dog. Which one of these has higher lattice energy? And it's going to be that magnesium chloride, again, because of the charges. So make sure you're paying attention to the charges. That's what I would always look at first. Okay, that's it. Y'all have a great day. We're done with chapter 9. Only one more chapter left.